Hello guys, this is the Meddude and today we're doing Edexcel Physics Unit 1, January 2022. So let's go right to it. So we have question number 1. So a student walked for 6 seconds. The displacement time graph for the student is shown. Okay, displacement, the time. Which row of the table shows the final displacement and the velocity of the students? So now let's look at the displacement. So displacement is always from 0. So from 0, we end at here. So from 0 to here, what's the final displacement? Final displacement is 2 meters. Let's check in the options if we have 2 meters. We have 2 meters. Is there anything else that has 2 meters? No. So that means this has to be correct just by process of elimination. Well, let's just work out the velocity just in case. So what's the velocity? We can take 2 points. So let's take this point and this point. We know velocity is displacement over time. So displacement, let's take this point is, displacement here is 1 minus 0. And time is 4 minus 2. So that'll be 1 over 2. So 0.5, 0.5, and you can see A is indeed correct. Okay, so we move on to question number 2. So question number 2 says, physical quantities may be vectors or scalars. Which row of the table is correct? Force, mass, acceleration. So force is a vector, mass is a scalar, and acceleration is a vector. So let's see which option that is. So we want a vector here. We know mass is a scalar. We know acceleration is also a vector. So all three of them, we need D. You can see D has all of the 3 ticks. So D is correct. Let's move on to question number 3. The velocity time graph for a particle is shown. Velocity goes from, so you can see it's linear, it's going down all the way to 0, and again going all the way down again. I don't know what, it's very linear. Okay. So which of the following is the displacement time graph for this particle? Just by memory, this is in fact a velocity time graph for a parabolic motion. This is actually the same velocity time graph for parabolic motion or a projectile. You may have encountered this type of motion. So we can say that the displacement time graph will also look very similar. So that indeed is in fact A. Alright, so A over here as well. Let's move on to question number 4. So the diagram shows a student during a parachute jump on a windy day. The vertical component of our velocity is 5 meters per second. The horizontal component of our velocity is 8. She descends at an angle theta to the vertical. So we got 8 meters per second to the right and 5 meters per second downwards. Okay. Which row of the table gives the expression of the magnitude and the angle of the student's resultant velocity? So we can work out the magnitude, right? The magnitude. So let's draw the triangle itself. So the triangle will look something like this. So we'll have here, here, and so this is the triangle. And the angle we're looking for is this angle over here. So we have this triangle, and this is 8, and this is 5. So the magnitude would be 8 squared plus 5 squared. Okay, let's see if there's anything like this. So 8 squared plus 5 squared. So not this one, not B. It has to be C or D. Now let's look at the angle itself. So the angle, let's look at it like this. Make it easier for ourselves. Theta, this is 5, this is 8. So from SOHCAHTOA, we can see that we have our opposite and adjacent that we have. So we have to use tan theta equals what? 8 over 5. So theta must be tan inverse 8 over 5. So let's see if there's anything here. Let's look at A. A has tan inverse 8 over 5. So it's not B, tan inverse 8 over 5, not D. So 2 ticks is C and D. Sorry, C. C. So the answer is C. Let's move on to question number 5. An object on the moon falls a vertical distance of 0.32 meters. from rest, so u equals 0 here, and a time t equals 0.63. Which of the following give the acceleration expression which gives the acceleration due to gravity on the moon in meters per second? So what do we have in our question? What do we have available in our question? So let's write it down. So SUVAT. So we have S is 0.32, U is 0, V we don't know, A we're trying to find out, and T we know is 0.63. So the only equation that we can use is S equals UT plus half AT squared. So 0.32 equals 0 times 0.63, which is just 0, plus half A times 0.63 squared. Let's rewrite this. So this would be 0.32 equals A times 0.63 squared all over 2. Now we need to make A the subject here. So we move the 2 to the other side, becomes 2 times 0.32 equals A times 0.63 squared. So A must be 2 times 0.32 all over 0.63 squared. Alright, so let's see if there's anything similar here. So is it A? Nope, we need something. What do we need on top? We need 2 times 0.32. So on the top 2.038, 2 times 0.32, 2 times 0.32. And the bottom we need 0.63 squared. That is C. The answer is C. The graph, question number 6. The graph shows how terminal velocity varies with mass for small spheres of equal diameter falling through a viscous liquid. Which of the following describes the gradient of the graph for a liquid with a greater viscosity? So what is the equation? The equation usually is F equals 6 pi r viscosity coefficient V. In this case, force is what? MA equals 6 pi r V. And what is the gradient? The gradient is V over M. So we can make that the subject. So it will be what? It will be A all over 6. What's left? 6 pi r coefficient equals what? V over M. So they're saying, what happens when you have a greater viscous liquid? What happens to the coefficient? This increases, right? This increases. So if this increases, that means V over M will now what? It will decrease. The gradient has to decrease because we're increasing the denominator. That means the gradient will decrease. This whole expression will decrease. That means the gradient will also decrease. So what does that mean? That means we'll get a smaller gradient. So we can say B. We get a smaller gradient for a greater viscosity. So question number 7. A person is pushing a trolley at constant velocity. The floor exerts a force P. So the floor exerts a force P on the person. So we can say P on the person, right? The person exerts the force Q on the trolley. So we can say Q on the trolley. And then you can say the trolley exerts a force R on the person. So trolley exerts a force R on the person. And the total drag force is S. So we got the total drag is S. Okay, so that's just the question. The question says, which pair of forces is a Newton's third law pair? So we need a force that equal and opposite. So you can see over here, just by looking at it, is Q and R. They're both equal and opposite. So Q and R is our answer. Let's move on to question number 8. A wire breaks when a tensile force T is applied. A second wire made of the same material has twice the diameter. Which of the following is the force required to break the second wire? So first, let's write down the formula. We know stress equals force over area. Force over area. Okay. In this case, we know the force is T, right? So the first one, so I'm just going to stress 1. Stress 1. We know it's T all over what? What's the area? Area we know is pi r squared, right? Pi r squared, right? So what about stress 2? What about the second wire stress 2? We know it has twice the diameter. What did that mean for the radius? That means the radius is now 2r, twice the radius. So that means t equals pi times 2r whole squared. So what does that mean? That means we now expand. So t equals 4 pi r squared. Now we have to compare it to, what? Now you have to compare it to the original stress one. We need to see what's the scalar multiple, right? So you can see that the difference between stress 1 and stress 2 is that this does not have a 4 here. So let's bring the 4 on top here. So we will get 4 stress 2 equals t over pi r squared. And we know this is stress 1. So 4 stress 2 equals what? Equals stress 1. So what can we say about the force required to break the second wire? It's 4 times the first wire, isn't it? So we can say that it's 4 T is required, right? So the answer has to be A. Let's move on to question number 9. A beam is balanced on 2 supports as shown. So we have P, there's a larger distance here, and then we have Q, smaller distance, so this probably is a bigger force. The beam has a weight W, okay, and the reaction forces at 2 supports are P and Q. Which of the following statements about the magnitudes of the forces is correct? P is greater than Q. That's not true because this is a greater distance. So that means P is probably lower than Q because there's a greater distance here than as opposed to here, right? So that's not right. Q is greater than W. We don't know whether the weight is greater than W or not. So we don't know whether Q is greater than W or not. So we can't say that. Okay. What about Q is greater than P? That is correct. So we got this conclusion right now beforehand. So we know this is correct. What about P? What about D? P plus Q is greater than W. Well, that's actually wrong because it says, the question itself says it's balanced. So P plus Q has to equal W. Okay, so this is also wrong. So what is the answer? The answer is C, because why? This is a smaller distance as compared to W to P. That means Q has to be greater than P for it to be balanced, right? Okay, now let's move on to question number 10. Which row of the table contains 2 units that are not equivalent? Okay, so let's just look at what we have here. So we have joules per second. So that's what? Energy over time, which is the same thing as power, which is watts. So they are equivalent. What about B? So we have kg meters per second. So that's mass times acceleration. So this is probably force. Okay. And Newton second. This is force times time. Okay, you can see this is force and this is force times time. So they are not equivalent. So this is probably the answer. Let's look at the other two. We have newtons per kilogram. So that's force over mass. That is acceleration. What about this? Meters per second. That's also acceleration. So these are equivalent. What about Newton meter? This is force times distance, which is work done. And this is also work done, which is in joules. So what is not equivalent? It's kg meters per second squared does not equal Newton second. So it has to be B. Let's move on to question number 11. A slow-moving asteroid A was hit by a fast asteroid B. Asteroid B was absorbed by the asteroid A as shown. So before collision, after collision. State the principle of conservation of linear momentum. This is actually pretty simple. All you need to remember is that the total momentum before equals total momentum after. And what is this? It's in a closed system. In a closed system. Pretty straightforward. Then we have part B. So this is our 2 marks. So saying this and then saying it's in a closed system. So before the collision, asteroid A has velocity 2.19 times 10 to the power of 3 and a momentum of 1.8 times 10 to the power of 17. Show that the mass of asteroid A is about 8.2 times 10 to the power of 13. So what do we have available? We have V and we have P. We know P equals mv, right? And we're trying to find m. So m equals P over V. So this would be what? What's P? P we know is 1.8 times 10 to the power of 17. And velocity is 2.19 times 10 to the power of 3. So when you put this in a calculator, what do we get? We get 8.219 times 10 to the power of 13 kilograms. And since we want to show this around 8.2, we round to the one more significant figure than 8.2. So that will be 8.22 times 10 to the power of 13 kilograms. All right. So now what? So that is the answer. Let's move on to part II. So we have calculate the velocity of the asteroids after the collision. Okay. So what can we say about what's happening here? So we know that first we have MB and VB, right? And we have MA and VA. And what happens to the asteroids afterwards? We know that it becomes what? The mass becomes MA plus MB, and they have a common velocity V. So we can rewrite this and say, MA UA, not VA, plus MB UB, which is the initial velocity, equals MA plus MB times V. And what are we trying to find? We're trying to find this. So why don't we rearrange to find V? All we have to do is now divide by this. So V equals all of that divided by MA plus MB. Okay, so now all we have to do is now input the value. So what is the mass of asteroid A? We just worked out it's 1, we have given it to us 1.8. No. What is this? MA times UA is what? It's P, isn't it? It's P of A, momentum. And what they have already given this to us, momentum. So we can just first input that. So that'll be 1.8 times 10 to the power of 17. What about mass of B? We know it's here. So 5.9 times 10 to the power of 12 multiplied by velocity of what? Velocity of B before the collision, which is this. So 15 times 10 to the power of 3 all over MA plus MB. We know MA is what? MA we worked out as 8.219. So let's use more accurate values. So 8.219 times 10 to the power of 13 plus, we know the mass of B is 5.9 times 10 to the power of 12. Okay, so now let's put this in a calculator and we will get the value 3048 meters per second. Okay, we want to round it, so we should always round this type of answer to 3050 meters per second. And that's your answer. Okay, let's move on to question number 12. So the diagram shows a lift system for moving people up and down a tall building. There is a counterweight to balance the weight. So there's a counterweight to balance the weight of the people of the lift. An electric motor is used to raise and lower the lift. Explain how the counterweight affects the amount of work required from the electric motor to raise the lift. Okay, let's explain this in terms of work done. Okay, so if we do not have the counterweight, the electric motor will have to pull a lot more, and will have to do a lot more work if this wasn't here. So we can say that work done from the electric motor, right, is reduced because because now the total work done is what? Is the electric motor plus the counterweight. So it helps reduce the load on the electric motor. That's it. Okay. Let's move on to part B. The electric motor raises the lift through a height of 40 meters. So that is height. And a time of 30 seconds. That's 30. The height is 40. Show that the output power is 12 kilowatts. So how do we do this? We know that the output power of the electric motor, right? We know total work done is electric motor plus counterweight. We're trying to find out only the electric motor. So how do we do this? So first we have to find both the counterweight and the lift, don't we? And we subtract them by each other. So let's find energy grav or E grav of the counterweight first. Counterweight. So this will be what? mgh. So mass of what? Mass of the counterweight 1300 times g, acceleration due to gravity 9.81, times what? Times what? Times 40 as well. Okay, that's good. Anything else? Yeah, this is going to be 510120 joules. What about E grav of the people, the lift, mgh. So this is what? 2250 times 9.81 times 40. We will get is, what is it? It's 882900 in the calculator. And we want to find out the output power. So the power is what? We know power is delta E over T, or work done over time. And work done in this case is the difference between the two, which is 28,290,2900. Take away 510120 divided by time, which is 30. Okay, so this is what this gives us. 16426 watts, and they watt in kilowatts, so let's divide by 1000. So power equals 12.426 kilowatts, and we say power because we want to show it's 12, so our answer should be 12 point something. So 12.4 kilowatts. So that's our answer. Okay, let's look at part C. The electric motor dissipates energy to the surrounding at a rate of 3600, which is the same thing as 3.6 kilowatts. Determine the efficiency of the electric motor. So efficiency is what? Efficiency is useful over total times 100. So in this case, the useful is the 12.4, right? It's 12.4. What about the total? The total is, they tell us that there's also energy dissipates to the surrounding. So 12.4 plus 3.6K times 100. And this gives us 77.5% or 0.775. Both are correct. So its efficiency, we can round it to 0.78. Alright, so that's the answer. Let's move on to question number 13. So we have the Tyrolean traverse is a technique for crossing a deep valley. The photograph shows the climber crossing the river using the technique. The climber moves along the rope suspended from a bank on either side of the river. Okay, we can see here the free body force diagram for the climber shown below. The weight of the climber is 650 newtons. So we can see 650 newtons here. And we have tension on both sides. So what do? Okay, show that the tension in the T is about 1.3 times 10 to the power of 3 newtons. Okay, so what can we say? What can we say? Okay, so if we want to resolve, and because we're going into the angle, this will be T cos 76 from this end plus T cos 76, and both of this equals 650. So we can say, what can we say? We can say that 2T cos 76 equals 650. And how did we get that? We got that from resolving inwards towards the angle. That's cosine of the angle. And we have two of them, so we add them. And all we have to do now is make T the subject, so 650 divided by 2 cos 76. And this is 1343 newtons, which is the same thing as saying 1.343 times 10 to the power of 3 newtons. And what did we say? To show it's about something, we need to show the answer must be 1.3, one more significant figure, times 10 to the power of 3 newtons. So T equals 1.34 times 10 to the power of 3 newtons. Alright, so that's the answer. Let's move on to part B. So the rope has an unstretched length of 120 meters. Okay, unstretched length, that's good. Then they tell us, determine the strain in the rope while it is supporting the weight of the climber. You may ignore the weight of the rope. So what are they trying to tell us? They're trying to tell us that, okay, so what is strain first? Strain is delta x over x, right? What is delta x? We're trying to find delta x. We know x is 120. We know this is unstretched length. Now delta x means this is when you have this is the most stretched. When it fully stretches, this is what happens. So we're trying to find out, what are we trying to find out? We know that this length is half of this, which is 60, right? And this length from here to here is 60 meters. Okay. What can we say about this length here when it's outstretched? Right? What can we say? We can say we can divide. So when we resolve this way, this was cos. So if we resolve this way, this is sine, right? So we can do 60 over sine 76. This will give us the stretched length, which is 61.8. And this is also 61.8. So when we add them, we get what? When we add 61.8 plus 61.8, we get, this is obviously decimal places, we get 123.67. So what can we say about delta x? Delta x is obviously going to be 123.67. Take away 120. This gives us 3.67. So our strain is 3.67. So our strain is 3.67 divided by 120. This gives us 0.031 ... So we can say the strain is 0.03. That's good. The next question says, the rope has a cross-sectional area of 3.14 times 10 to the power -4. Okay, so this is area. Then it says, determine the Young modulus. We know Young modulus is what? Young modulus is stress over strain. We know stress is what? It's force over area. We know strain is what? 0.03. We already know. 0.31. And then what? Do we know the force? Yeah, we do. It's over here. So we can input it. So now it's 1.34 times 10 to the power of 3. We know the cross-sectional area is 3.14 times 10 to the power of -4. What about the strain? Strain is divided by 0.03. So when you put this in the calculator, what value do you get? We get 137 1.61804 Pascal. This is very large. So can we round this? Yeah, we can. Let's round this. This will be 1.38 times how many? 10 to the power of. So 1, 2, 3, 4, 5, 6, 7, 8. So 10 times 10 to the power 8 pascals. And then we round it to 1.4 times 10 to the power of 8 in the answer. Okay. So that's the answer for Young modulus over here. Let's move on to question number 14. So question number 14 says, a student of weight 600 newtons is standing on weighing scales in a lift. The scales are calibrated to give the readings in newtons. So we have the lift here, the weighing scales here. The lift moves upwards at a constant velocity, then decelerates to rest. As the lift moves, the student looks at the readings on the scales. Explain the readings on the scales. So the first thing we need to understand is that the person exerts a downward force, which is its weight, and the scale exerts an upwards force called F Newton, or normal force, right? And the scale actually reads, so the scale actually reads the normal force, and this is based on what? This is based on where the elevator is moving, right? So now let's look at the forces in the y directions, okay? So we know that the sum of all forces in the y direction is what? It's plus, we're taking up as plus, so it's plus the normal force, take away the weight, right? We already know the weight, but we're just doing this mathematically first. So the sum of all forces is going to be what? Mass times the acceleration in the y direction equals our normal force, take away mg. So we add mg to both sides, and we can say that the normal force is dependent on what? It's dependent on m, ay plus mg. We can take m as a factor. So acceleration plus g is our normal force. So what is the scale's reading dependent upon? It is dependent on this. We know the mass is constant. So what is it really dependent on? It's dependent on the acceleration of the lift. Okay, so now let's look at what they're saying here. So they're saying the lift moves upward at a constant velocity, then decelerates to rest. So what can we say in the first thing? So when it starts, we can say at rest, right? At rest, because nothing's moving, we don't have any force, we don't have any resultant force. We can say the scales will read 600 newtons. That's pretty straightforward. What about at constant velocity? At constant velocity, the scales will read what? Scales will read. So when you have constant velocity, what does that mean? When you have constant velocity, that means what? There is no resultant force, right? So what can we say? We'll read the same. So we'll read 600 because there is no resultant force. So the scales will read 600 newtons. Okay, so when it accelerates or when it's decelerating, what happens to Fn? So let's look at this. So when the lift decelerates, the acceleration in the y direction begins to decrease. So the normal force, and we said it's m ay plus g, and because this decreases, the normal contact force also decreases. So we can say So the normal force starts to decrease, meaning what? What does it mean? Meaning the scales will read less than 600. Because why? Because the normal contact force, or the normal force, is less than W. And scales, we said earlier, reads what? The scale actually reads the normal force, not the weight. It reads the normal force exerted on the person. So we can say that. All right, so we can also state that we can also write this in the answer as well. So we can say, because since the scales actually read the normal force, not the weight of the person, not necessarily the weight of the person. Okay, so that's question number 14 done. So we started with what? We started to explain that the person exerts a force W onto the scales, and this force W is contracted by this force we have N, Fn. And we said that the scale actually reads the normal force instead of the weight itself. Because we're in a lift, and because it moves up and down, we can now use Newton's second law of motion, which is sum of all forces. So we took upwards as positive. So the normal force minus W, because this is in the opposite direction. Then we said mass times the acceleration in the y direction is equal to what? Normal force minus mg. We got a formula for the normal force, which is in fact what the scale reads. And then we said at rest, obviously we don't have any acceleration, right? It's equal to the weight. So the scales will read 600. So at rest, we can say that Fn equals W. And at constant velocity, same. We don't have any resultant force. So at the same time, in both the scenarios, the normal force is equal to the weight. But in the third scenario, when it decelerates, we know that the acceleration is decreasing, right? That means the normal force is decreasing. That means the scales have to read less than the weight, because it is less than the weight, isn't it? The normal force is less than the weight. So yeah, let's move on to question number 15. So a hollow brass cylinder with closed ends is floating on the surface of the water. The cylinder has a length of 4 centimeters. We got 4 centimeters here, and an external diameter of 2.1 centimeters. So we can say the radius is this divided by 2, r. So r is 2.1 divided by 2, which is 1.5 centimeters. So r is 1.05 centimeters. Okay. Now what? Then they tell us 63% of the volume of the cylinder is submerged. So the volume here is 0.63 times the actual volume of the cylinder. So we got VC. The cylinder contains negligible weight of air. Explain why the brass cylinder floats. So why does ice float? Because why? Why does ice float? Because we say that ice is less dense than water. So what can we say about density of brass cylinder? We can say density of brass cylinder is less than the density of water. What else can we say? Are there any forces acting to make this afloat? Yes, there are. There is the weight of the cylinder, which is contracted by the upthrust. So what can we say? We can say as well as weight of the cylinder of cylinder is equal to the upthrust. So those are our 2 marks. Part B says the density of water is 1 times 10 to the power of 3 kilogram per meter cubed. Show that the mass of the cylinder is about 9 times 10 to the power negative 3. So what can we say? Let's just write down what we know. Density is mass over volume. And we know mass is density times volume. Okay, so we know the density of water, which is 1 times 10 to the power of 3. What about the volume? We know that the volume is what? Is 63% is submerged. So we can say the volume is 0.63 times VC. And what is VC? VC we know is, how do you find a volume of cylinder? Is pi r squared h. So what is r? R we said is 1.05 centimeters. And the height, in this case, is the length, which is 4, right? That's 4 centimeters. Now we can't deal with centimeters because there's meter cube to meter to the power of minus 3. So what do? We divide by 1,000. So this will become, so we divide by 10 to the power of 3. And this becomes what? We divide. This becomes 0.0105. And this becomes what? 0.04 meters. So let's work out this 0.63 times VC. So VC is pi times 0.0105 squared multiplied by 0.04. And all of this we multiply here. Over here. And this we get is, so this is 1.39 times 10 to the power of negative 5. And same thing here, so 0.63 multiplied by 1.39 times 10 to the power of negative 5. This gives us 8.757 times 10 to the power of negative 6. We get this value and we input it here, over here, to find the mass. And the mass equals 1 times 10 to the power of 3 times by 8.757 times 10 to the power of negative 6. We get 8.757 times 10 to the power of, because there's 3 in minus 6, this becomes minus 3. And do we round it? Yes, we do. So mass equals, so we round it to 8.8 times 10 to the power of negative 3 kilograms. So that is the mass of the brass cylinder. Why? Because we want to round to 9, so we need to go 8 point something, which is above 5 times 10 to the power of negative 3 is what we need to show. Alright, let's move on to part II. Deduce whether an identical hollow cylinder made of gold would also float. Assume that the volume of gold is the same as the volume of brass. And they've given us both densities. So they're saying volume of the cylinder, brass cylinder, is equal to the volume of gold. Okay, so what can we do with that information? Can we find the volume of gold needed? It has to be similar to the volume. So this, we should get a volume that's same as this for it to float, right? For the gold to float. So let's see if we can get this volume of gold. So how do we get volume of gold? Volume of gold is how? How do we get volume of gold? Can we get it somehow or not? Volume of gold that is submerged in water, obviously. We can get volume of gold normally. Let's see if we can get this. So we have what? We know that volume of the cylinder, brass cylinder, we know density equals mass over volume, and volume is mass over density. So mass of brass is what? Mass of brass we worked out 8.757 times 10 to the power of negative 3. And we worked out the volume, sorry, the density is same 8.7 times 10 to the power of 3 from here. Equals 1.001 times 10 to the power of negative 6 meter cubed. So we know the volume of C. So this volume is now equal to what? Same thing as volume of gold. So this is the same thing as volume of gold that we need. So we can find the mass of gold, which is density of gold multiplied by volume of gold. And then we can divide by the density of water, so to find whether it's greater or less than 1.39 times 10 to the power of negative 5. So what is the density of gold? They tell us is 19.3 multiplied by 10 to the power of 3. And do we know the volume? Yes, we do. 1.001 times 10 to the power of negative 6. So when you multiply them, we get what? We get 0.0194 kilograms. And what did we say? We did the same thing here, right? We want to find out this, is it greater or less than? We need to find out the volume. The volume we know is mass over density. And in this case, we're looking at density of water. So 0.0194 divided by 1 times 10 to the power of 3. It gives us 1.94 times 10 to the power of negative 5 meter cubed. So let's compare the values. So this is the value we got, 1.39. That's the volume that's allowed to be submerged. This is the volume that we can have that is not submerged, but this is the volume of cylinder that is allowed so that the cylinder floats. And this volume is greater. That means what? 1.39 times 10 to the power of negative 5. So does it float? Does it float? Yes or no? It's greater than 1.39 times 10 to the power of negative 5. So what can we say whether it floats or not? We say that it sinks. That is the final answer. Okay, let's move on to question number 16. So the photograph shows a toy pinball machine. The launcher is pulled back, compressing a spring. The spring obeys Hooke's law. When the launcher is released, the spring returns to its original length and a small ball is launched horizontally into the machine. Pretty good. So now what can we say? They're saying when the launcher is pulled back, so when the spring is pulled back, the spring is compressed by 5 centimeters. So delta x is 5. Delta x is 5? Yeah, delta x is 5. Then what can we say? 5 centimeters, so this is centimeters. When the spring is released, the ball is launched at 8 centimeters per second. Show that the kinetic energy is about this. So we need to show that the answer is what? The answer is 3 point something times 10 to the power of negative 5 joules. Okay, so how do we do this? So we know EK, the formula is half mv squared. We know half. Mass we can't do in grams, so we have to divide by 1,000 to get kilograms. Velocity, they're giving us in centimeters per second. We want in meters per second, so we have to divide by 100. And we square it. And we get what? We get 3.84 times 10 to the power of negative 5 joules. And what did we say? We say that we want only one more figure. And then after 3 point, we need one more figure after 3. That will be EK equals 3.8 times 10 to the power of negative 5 joules. This is our answer. Alright. Determine the force on the ball when the spring is released. Do we know a formula that we can use to find the force? What we do know is EL is half times force times delta x. And we already know what EL is, the same energy. So we can rearrange to find F. That'll be 2 multiplied by EL divided by delta x gives us force. So force equals 2 multiplied by 3.84. We use more precise values in the actual calculations. Minus 5 divided by what? What's the extension? We know the extension is what? 5 centimeters, or 5 divided by 100, which is 0.05 meters. So 0.05. And we get 1.536 multiplied by 10 to the power of negative 3 newtons. Now, what did we round to? We round to 1.5 times 10 to the power of negative 3 newtons. Why? Because look, we rounded to 3.8 here. We're technically using the same value, so this must be 1.5 times 10 to the power of negative 3. That's the answer for part B. Let's move on to question number C. So we have determine the stiffness of the spring. So how do we determine the stiffness of the spring? We know that F equals K delta X. Straightforward, we can now rearrange F over delta X. You know, F is what? From the previous question, this one over here, we use more exact values in our calculations. So 1.536 times 10 to the power of negative 3 divided by 0.05. This gives us 0.03072. What about the units? This is in newtons, this is in meters. So it's be Newton meter minus 1. We can now round this to 0.03 Newton per meter. Alright, then it says the spring returns to its original length L. Sketch a graph on its axis to show how the velocity varies with the length of spring. So when we compress it, we're actually going backwards, and we reach around here, and this is what? L minus 5. And let's say we're doing length of the spring, we're doing in centimeters, and the velocity we're also doing in centimeters per second. So we start at L minus 5, right? When we compress it, right? What did it tell us? When you compress it, that's when it's about to get launched. And then it's launched at a speed of 8. So by the time it decompresses to L, we should be around 8. So we should be around 8 centimeters. Not 8 centimeters, but 8. So over here, we should be around 8. At when it's L, we should be around 8. Okay, so is it a straight line? No, it's not a straight line. It's actually a parabolic motion because you're exponentially increasing your speed. So it looks something like this. Nope. Something like this. All right. Okay. So L minus 5, 1 mark, 8, 1 mark. That it stops at L. It stops at 8. Not stops, but it comes at 8 when it's at L, and the shape of the graph. That's your 4 marks. All right. Let's move on to question number 17. A small sphere is moving horizontally through a viscous liquid. Stokes' law can be used to calculate the drag force on an object. State the conditions that must apply for Stokes' law to be valid. So what are the conditions? Conditions are object must be able to show laminar flow, and usually it's a sphere. An object must be a sphere. Object is a sphere. Must be a sphere. So that's one condition. That's the second condition. there is a constant force of 2.3 times 10 to the power of negative 5 acting horizontally on the sphere. Diameter they've given us, right, is here, so the radius will be 4.5 times 10 to the power of negative 3 just divided by 2. This is the force given to us already, and this is the viscosity, and they've given us V. Calculate the horizontal force. Very straightforward. F equals 6 pi r viscosity V, 6 pi multiplied by 4.5 times 10 to the power of negative 3 over 2 multiplied by 7.1 times 10 to the power of negative 2. And we know the velocity is 5.2 here. So 5.2 times 10 to the power of negative 3. So what does this give us? This gives us what? What does it give us? This gives us, the force is what? This gives us 1.56 times by 10 to the power of negative 5 newtons. Or we round it because we're also looking at this. This is the other force that's acting. So we should round it to that force. So that will be 1.6 times 10 to the power of negative 5 newtons. So what is the resultant force? Let's say delta R, or resultant force, delta F, is 2.3 multiplied by negative 5. Take away 1.6 times 10 to the power of negative 5. This gives us 0.7 times 10 to the power of negative 5 Newton, which is the same thing as saying 7 times 10 to the power of negative 6 Newtons in standard form. So we got this. All right. Calculate the maximum speed of the sphere in the horizontal direction. We know the maximum speed must have the maximum force, and the constant force is this much. Right? This is when you have no force acting. Okay, so we can say that 2.3 times 10 to the power of negative 5 equals our 6 pi r v, and we're trying to find v, right? So we can say 6 pi multiplied by r, which is 4.5 times 10 to the power of negative 3 divided by 2. And now this viscosity coefficient 7.1 times 10 to the power of minus 2 times v. We're trying to find v, so v will be 2.3 times 10 to the power of negative 5 divided by all this. We divided by all this, so copy. So it'll be divided by all of this. So 2.3 times 10 to the power of negative 5 divided by 6 pi times 4.5 times 10 to the power of negative 3 divided by 2, which is the radius, multiplied by 7.1 times 10 to the power of negative 2. We get 7.638 times 10 to the power of negative 3 meters per second, which we can round to 7.6 times 10 to the power of negative 3 meters per second. So that is our max horizontal speed. Alright, then we can say part C, a larger diameter sphere in the same liquid is acted upon by the same constant force as in B. The liquid is at a lower temperature. Explain the effects these changes will have on the maximum speed of this sphere. So the first thing I noticed is the larger diameter means what? The radius is increased, right? And we know that we're talking about V here, and we know F equals 6 pi r V. I know V is force over all that, 6 pi r V, not V, just that. So we can say since radius is larger, right? Radius up. All right, what can we say? Since radius is larger, and what else is happening? And the liquid liquid is at a lower temperature, so what happens to the viscosity coefficient? Lower temperature, which means what does it mean? It means that the viscosity increases. It means viscosity increases, so V equals F6 pi and R increases and viscosity coefficient increases, so V goes down, so velocity decreases, which means max speed will decrease. Alright, so that's the answer. Let's move on to question number 18. So we got a stunt motorcyclist wants to jump across a river to land on the other side. The diagram shows the motorcyclist driving off a ramp at the edge of a river. The ramp is at an angle of 25 degrees to the horizontal, and the height at the end of the ramp is 3 meters. The width of the river is 100 meters. The initial velocity is the motorcyclist is 35 meters per second. Okay, so we know 35 meters per second. Calculate the horizontal. So calculate the horizontal and vertical. Calculate the horizontal and vertical components of the initial velocity as it leaves the ramp. Okay, so that's pretty straightforward. We know that, what do we know? We know that this over here is V cos 25 and vertical is V sine 25. So we can say Vx is V is 35 cos 25 and Vy is 35 sine 25. So this gives us what? So Vx gives us 31.7 meters per second and Vy gives us 14.8 meters per second. And since they have rounded to 2 sig fig, so we should also do the same. 32 meters per second for horizontal, 15 meters per second in the vertical. So next part says, deduce whether the rider lands on the other side of the river. So I got the diagram here so we don't have to look back. So we know that the Vx is over here that we worked out is what? Is 32, right? Vx is 31.7. Vy is 14.8. So can we do something that can help us find out whether the rider lands or not? What can we do? Can we do something or not? We can, can't we? So we can find out whether he lands or whether he falls, right? We can do it. We can find out the vertical, like at the end, whether he's here or not. How do we do this? First, we need to find how long it takes for him to travel 100 meters. We can only do that with what? Distance is Vx times time. So we know 100 equals 31.7 times time. Time equals for the rider to travel 100 meters is 100 divided by 31.7. This gives us 3.15 and there's a big decimal seconds. Okay, so now we know the time. Now we look at the vertical direction. So what do we have? SUVAT. We want to find out S. We want to find out S. Do we know U? Yeah, we do. Is VY. Do we know final velocity? We don't. We know A is minus G. And we know T is 3.15 seconds. So what equation do we use? We can use S equals UT plus half AT squared. So we can use Vy, which is 14.8, right? 14.8. So we can use 14.8 multiplied by 3.15 plus half 9.81, which is negative, times t squared, which is 3.15 long decimal squared, which you just use in a calculator. And then when you get, what do we get? We get negative 2.12 meters. So that means he went from 3, he went down negative 2.12 meters by the time he reached 100 meters. So 3 take away 2.12 meters. This gives us what? This gives us what? This gives us what? This gives us 0.88 meters. So what can we say? We can say, so the rider lands on the other side of the river, right? Because he's still at 0.88 by the time he reaches the next part. So next part says, explain how air resistance would affect the jump. So what does air resistance do to the jump itself? What does it do? We can say, let's look back at the diagram here. We can say, let's just get rid of this line. The air resistance, instead of this motion here, we will have a motion that something like this, right? So air resistance will probably make it land it won't make it land in the river, and it will be slower. So what can we say about air resistance? We can say air resistance goes against the motion of the motorcyclist. What else can we say about him? So the speed, right? So this, we're talking about horizontal speed, right? Speed in the horizontal direction. Decreases. So the motorcyclist doesn't travel as far horizontally. Okay, so one mark is saying it goes against the motion. Second part saying it decreases the speed, and which leads to that he doesn't travel as far horizontally, or reduce in horizontal distance traveled. So this is the end of the paper. Thank you guys for watching. Please be sure to join the Discord, and I will see you guys in the next video.